Hello everyone, my name is Ankit and today we will be talking about how to automate merges to keep your builds healthy. Before we go into the details, a little bit about my background. I'm co-founder of Aviator. We are building developer workflow automation platform. Previously, I've been an engineer in several companies including Google, Adobe, Shippo, Homejoy, and Sunshine. You can also find me at Twitter at AnkitXG. So the first question you will be asking is merging. How hard can it be, right? All you have to do is press this green button and your changes are merged. Well, let's take a deeper look. Before we go into details, let's think a little bit about different repositories that teams use. So we have monorepos where all the entire engineering team is using a single repository. And then we have polyrepos where every team within a company may be using a separate repository. In case of monorepo, the advantages you typically have is easier to manage dependencies. You can easily identify vulnerabilities and fix everywhere together. It's easier to do refactoring, especially if it is cross-project. You have a standardization of tools, as well as code sharing becomes important. You can share the same libraries across different projects. In case of polyrepos, some of the advantages are simpler CI/CD management. Everyone has their own different CIs. So there's lesser build failures. You have independent build pipelines. Build failures typically are localized within the team. In this particular context for this conversation, we will primarily be focusing on monorepo and identifying what are the challenges in a large team when you're working on a monorepo. So the first question you would probably want to ask is how often do your mainline builds fail? And is your current CI system enough? There are several reasons why your mainline builds may fail. For instance, there could be stale dependencies between different changes that are merging. There could be implicit conflicts, two developers working on similar code base. You can have infrastructure issues. There could be issue with timeouts. There could be both internal as well as third-party dependencies that can cause failures. Obviously, there's race conditions, shared states that also cause flaky test. In this particular conversation, we will primarily be talking about the stale dependencies and implicit conflicts and why those things are important to think about. So to give you an example, let's just take an example of why this is important in a monorepo case. So let's say there are two pull requests where they're merging together, or they're based out at two different times from your main, and both of them have passing CI, but eventually when you go and merge those changes, the mainline fails, right? This could happen because both of them may be modifying the same pieces of code where they may not be compatible with each other. And the challenge is as your team grows, these kind of issues become more and more common. Eventually, there will be teams setting up their own build police, to make sure that if a build fails, that there is somebody responsible to actually fixing that. There will be typically people will do rollbacks, releases get delayed. There could be chain reactions where people are basing off of failing branches, and then eventually they'll have to figure out how to actually resolve those issues. And these kind of failures increase exponentially as your team size are growing. And that's why it becomes very critical at a certain point in your team to make sure you can actually take care of it so that developer productivity is not significantly impacted. You don't want a situation where everyone is just waiting for the builds to become green, they cannot merge any changes because builds are always broken, and you're losing important developer hours. So then what's the solution? The solution is merge automation, where many companies, for instance, you may have heard of GitHub launching their own merge queue. GitHub also has something similar called merge train. There are some open source versions that exist today, like Boars, that can also provide similar capabilities. So we'll be diving more into how this merge automation works and how you can adopt that internally. To give you a very simple example, let's take here that instead of so let's see this pull request, which is PR1. Instead of developers manually merging these changes, they would typically, inform the system that it's ready. And at that point, instead of like merging changes itself, the system would actually merge the latest main into this pull request and then run the CI. The advantage here is you're always validating the changes with the most recent main. Now, if the CI passes, this PR will get merged. And meanwhile, let's say there's a second PR that comes in while the CI is running, it's going to wait for the first PR to merge before it picks up the changes of the latest main, and then will process and run the same thing. So once the second PR passes also, it's going to merge the same way. Let's kind of like look at some of these stats. Let's assume for sake of this conversation that the CI time is about 30 minutes. Your pull request, you're merging in a small team, is about 10 PRs a day. This would take about, if you kind of like run it serially, it will take about like 5 hours because you're waiting for each PR CI to pass before running the second one. The total amount of CI you'll run is about 50. Now the challenge is if you're in a big team where you're merging 100 PRs a day, in the same amount of CI, if it takes the same amount of CI, now you're looking at completing about 50 hours of merge time. Now, this is unrealistic for any kind of like system to be able to merge changes this slowly. So then, can we do better? One way we can think about doing this better is by batching changes. So instead of merging one PR at a time, what your system can do is it can wait for a few PRs to get collected before running the CI. The advantage here is you're creating these batches, which essentially make sure, like, one, you're reducing the number of CI that you're running, but also it helps reduce how quick, like, essentially like help reduce like how long is the wait time. So in this case, if the CI passes, it's going to merge all 4 of the PRs together. Now considering like all of them eventually pass the build. And in case there's a failure, we are going to bisect these batches so that we can identify which PR is causing the failure and merge the rest of them. Now here, you can imagine like it's going to cause a little bit of slowdown in the system. So let's look at the stats. In case there is no failure, let's say best case scenario, if you're doing a batch size of 4, now your total merge time suddenly drops from 50 hours to 12.5 hours. Now that's a significant improvement, and also the total number of CI runs are going to be small. Now, but in a real scenario, right, you're going to have failures. So if there is even a 10% failure rate, you see like the merge time increases significantly. So you're like waiting like 24 hours for all your CIs to merge, all your PRs to merge, and the total number of CIs also increase significantly. So then the question is, can we still do better? So we are going to think a little bit about think of merges slightly differently. Instead of thinking of merges kind of like happening in a serial world, you think about this as like parallel universes. By parallel universes, what I mean is like, if you think of main as not like a linear graph or like a linear path, you think of this as like sort of several potential futures that the main can possibly represent. To give an example, let's think about the optimistic queues. So let's say your main is at this particular point, a new PR comes in, it's ready to merge. So what we are going to do is something similar to before. We're going to pull the latest main line and create like this alternate main branch where we run the CI. Once the CI passes, we are going to eventually like similarly merge the changes. But here, what we're doing is like imagine while the CI is running, a second PR comes in as well. So instead of waiting for the first CI to pass, we optimistically assume that the first PR is going to pass. And in this alternate main, we're going to start a new CI with second PR as well. So once the PR for the first one passes, it's going to eventually merge. And likewise, if as soon as the CI for the second one passes, it's going to merge as well. Sorry, it's been a bit slow. So it's going to merge as well. Now, obviously, here we are looking at like what happens if the CI for the first one fails. If the CI for the first one fails is what we're going to do is we're going to reject this alternate main and essentially create a new alternate main where we're going to run the rest of the changes and follow the same pattern. And in this particular case, we're going to make sure the PR1 does not merge and cause a build failure. So in best case scenario, given that we're now not waiting for any CI to finish, you can technically merge all your 100 PRs in less than an hour. Obviously, in case of a median case where we expect like 10% of the PRs to fail, your merge time is still very reasonable. Now you're merging in 6 hours instead of the 12.5 hours that we were seeing before. And alongside, your CI runs are slightly higher in this case because you can possibly running this multiple CIs at the same time. So then the question is, can we still do better? One way to improve on this is combining some of the strategies we've discussed before. So let's say if you combine the strategy of optimistic queue with batching. So instead of running instead of running a CI on every PR, now we kind of like combine them together. So essentially you're running like these batches of PRs, and like again, as they pass, you merge them. If they fail, you split them up and identify what causes a failure. Let's look at the stats again. So now we are saying the total merge time is still less than 1 hour, but what we have done is we have reduced the total number of CIs to 25 instead of 100. And even in the median case, the merge time is lower from 6 hours to 4 hours, and your total number of CIs are still lower. So can we still do better? Now let's think about like some more concepts here. One of the concepts is predictive modeling. But before that, let's think about what happens if we assume all possible scenarios of what the main could look like if a particular CI is going to pass or fail, or PR is going to pass or fail. So in this case, like we have represented these 3 PRs and all possible scenarios where all 3 of them merge, 1 of them merge, or 2 of them merge. And if you run these, essentially if you run in this way, then we never have to worry about like failures because we are already running all possible scenarios and we know one of them is going to be successful. Although the challenge here is obviously running a lot of CI, right? We don't want to be running too much CI, and this is where it can be interesting. So instead of like running it on all of them, what we can do is we can calculate a score, and based on that, essentially identify which ones are worth pursuing, which paths are worth pursuing. So you can do optimization based on lines of code in a PR, types of files being modified, test added or removed in a particular PR, or number of dependencies. So in this case, we have specified the cutoff as 0.5. And as you can see, we're running only a few of these. Excuse me. We're running only a few of these builds paths, and that by reducing the number of CI. So now you're obviously asking, can we still do better? Now we're going to think about like concepts of multi-queues. So this is applicable in certain specific cases where we can understand like different builds. So instead of like thinking of this as a singular queue, now we're going to think of this as like, many different paths you can take and like many disjoint queues that you can run. So we use this concept called affected target. So there are systems like Bazel that actually produce these results or like these affected targets. So essentially, if you can identify what builds within your primary repository that a particular change impacts, you can create disjoint queues where all these queues can be independently run while making sure your builds are not going to impact it. So let's assume that there are like 4 different kinds of builds that your system produces, A, B, C, and D. And this is kind of like the order of the PRs that they came in. You can potentially create 4 different queues out of it. So let's say kind of like the PRs that impact A are in first queue, the PRs that impact B are in second queue, and so on. So one thing to note here is a PR can be in more than one queue if it's impacting more than one target, and that's totally fine. So essentially for PR4 or PR5 to pass, in this case, it needs to wait for PR2 to pass or fail. But at the same time, we are still making sure that in a worst case scenario where a PR fails, we are still really not impacting all the PRs in the queue, but only the ones which are behind that particular queue. This definitely increases the velocity at which you're merging the changes, because it's in some ways localizing failures to a particular affected target. So this is a great example where we are looking at two separate queues. Let's say one target is backend, one target is frontend, and there are multiple PRs queued, but they can independently be compiled and run while making sure that you're not impacting, one change is not impacting the other one. And that way you can run them parallelly as well as, merge them while not impacting the builds. So now, can we still do better? There are like few other concepts that we can think about to actually make it further optimize these workflows. So one of them is thinking about reordering changes. For instance, you can select the high priority changes or the changes where there's lower failure risk and put them ahead of the queue. The advantage here is it's not going to cause a possible chain reaction of failures, and it's going to kind of like reduce the amount of possible failures you can have. You can also kind of like order it based on priority, something which is like, really big change. You can probably like say it's going to be lower priority and we're going to pick it up later. There are other concepts of like, for instance, fail fast. So you can reorder the text execution. The ones which typically fail more often, you probably want to run it sooner. That way, as soon as the PR gets queued, you identify these failures and are able to fail fast. The other things you can do is you can split the test execution. This is what many companies do, where they will run many of the fast tests before merging and making sure kind of like, these are the ones which are more critical or things which possibly fail more often. And then run the smoke test or like things which typically are stable but maybe slower, but you run them after they're merging. Obviously, you expect like the tests you're running after merge fail very, very rarely. But if it fails, you can just like roll back. So essentially, you're trying to find the best of both worlds to make sure your builds are generally passing, and very rarely if it fails, you have a way of automatically rolling it back. So that's about it. I'm going to share a little bit about like some of the other things we at Aviator work on. So we also support like scenarios of Poly-repo. To give you a very quick example, let's say you have like different repositories for different types of projects, and you're kind of like merging a change. Let's say you're modifying an API that's going to also impact like how you merge, how that API interacts with web, how it interacts with iOS and Android. Now here, the issue is, let's say you make this change, which kind of like requires all of them to be modified, but like you merge 3 of them and 1 of them fails. Now this can cause eventual inconsistency. And we have like essentially, our system essentially like ensure we have a workflows, we call it chain sets, that essentially combines or like defines these dependencies of changes across the repositories. So you consider them as like single atomic unit. So essentially, we make sure all of these PRs either merge all together or none of them merge at all. We also have a system to manage flaky test. As you can imagine, as your system and team grows, everyone is very familiar with flaky tests. Your system becomes unstable. You'll have like these shared states or inconsistent test behaviors where your test may fail even though you may not have made any change related to that. So what our system typically does is we identify all these flaky tests in your runs and essentially like provide with a customized check that you can use to essentially automatically merge the changes. So what we typically do here is we identify whether a particular flaky test which has happened is related to your changes or not. If it is not, then we suppress that test in the test report so that you get a clean clean build health, and then you're able to merge that changes. So this works very well when you're thinking about like automatic merging, because you can use this check as a validation to make sure your systems are still healthy. We also have capabilities to manage stacked PRs. So if you have like PRs which are stacked on top of each other, we have capabilities through which you can automatically merge these changes, as well as like there's a CLI to, sync all your stacked PRs together, as well as like be able to like queue all of the PR to be merged together. And again, kind of like it follows similar patterns of chain set that we described. So we automatically are able to identify dependencies of all these stacked PRs and consider them as atomic units. So all of them merge together or none of them merge at all. I think that's about it. So thank you very much. These are some of the references that we use for this talk, but I really appreciate you spending time listening to this. If you have any questions, you can always reach out to me. My email is ankit@aviator.co. Let me see if this is going to the next screen. And yeah, like check it out. Check us out at Aviator. We do automatic merging as well as like many other capabilities, many automated workflows for developers. If you have any questions, you can, as I said, you can reach out to me. You can also send me a DM on Twitter. Thank you and have a great day. Bye.